There are moments in Earth's history when everything we understand about life, about how the planet works, simply collapses. Not gradually, not over millennia. In an instant, a geological instant. And then the world has to start over. These are the periods we never talk about. The dark ages of our planet. The times between the world we think we know and the world that had to rebuild itself from nothing. Most people think about human history as deep. We go back thousands of years, and we feel like we're looking into the distant past. We study ancient Egypt, ancient Rome, ancient China. We think about empires rising and falling. We think about civilizations that lasted centuries or millennia. That feels old to us. That feels ancient. But the past we're about to explore stretches back tens of millions of years. Millions. Think about what that means. Your entire frame of reference for time is measured in seconds, minutes, hours, days. A year is almost incomprehensibly long to us. 1,000 years feels like forever. 1,000,000 years is so far beyond human comprehension that we can barely even wrap our minds around it. Try to imagine it. 1,000,000 individual days, 1,000,000 individual nights, 1,000,000 individual sunrises and sunsets and rainfall events and animal births and deaths. And we're talking about not 1,000,000 years, but tens of millions, dozens of them, stretching back into deep time. 66 million years ago, something happened that would divide Earth's history into before and after. A before world where dinosaurs had ruled for over 160 million years. An afterworld where they would be gone and the planet would belong to something else entirely. But that catastrophe, as terrible as it was only the beginning of a story we still don't fully understand. What came after was stranger, more mysterious, and in many ways more important than the impact itself. And if you're using this video to fall asleep, perfect. That's exactly what it's for. So, maybe hit subscribe and drop a comment telling me where you are and what time it is. I genuinely love checking those. It's wild seeing London at sunrise, New York at lunch, Los Angeles at midnight, all watching at the same time. Because in the millions of years that followed, the world didn't just recover, it transformed. It became something it had never been before. Ecosystems that had never existed were born and died. Species appeared and disappeared within the span of millions of years, too fast to see, but too slow for us to truly comprehend. The very fabric of life on Earth was rewritten, and most of it happened in darkness, in the fossil record's great blank spaces, in the gaps between the things we've managed to find and preserve. We're talking about a hidden age, a prehistoric dark age that shaped everything we see today. The age of mammals rising from the ashes of extinction. The age of strange creatures that have no modern equivalents. The age when the stage was being set for everything that would eventually come, including us. So tonight, let's venture into that hidden world. Let's explore the dark ages that transformed our planet. Let's talk about the time before humanity rose, before we ever walked this earth, when life itself was still figuring out how to survive in a broken world. The story begins with an ending. 66 million years ago, an asteroid the size of a mountain slammed into the Yucatan Peninsula with an impact that was incomprehensibly violent. We're talking about a rock roughly 6 miles across, traveling at speeds that would make even the fastest spacecraft look stationary. The energy released was equivalent to millions of nuclear weapons detonating simultaneously. Try to picture what that means. In a fraction of a second, the asteroid vaporized. Rock that had been solid ground for millions of years turned into superheated vapor. The temperature at the impact site exceeded the surface of the sun. All that energy had to go somewhere, and it went up A plume of debris, vapor, and pulverized rock shot into the upper atmosphere and circled the planet within hours. The impact created a crater over 90 miles wide. That's not a crater. That's a wound in the planet itself. Fires erupted across continents. Forests thousands of miles away spontaneously combusted. The sky turned red and black with ash. Everything within hundreds of miles of the impact site was instantly annihilated. But here's what most people don't understand about this event. The immediate devastation, as catastrophic as it was, wasn't actually the worst part. It was what came after, the consequences, the domino effect. The debris that filled the atmosphere blocked out the sun. For months, maybe longer, darkness covered the entire planet. We're talking about a kind of darkness that had never existed before in the age of dinosaurs, not since life had first crawled out of the oceans. Not a cloudy day, not a solar eclipse, total darkness. Photosynthesis became impossible. Plants died first. Without plants, the herbivores starved. Imagine being a triceratops. You're a massive animal that needs hundreds of pounds of vegetation every single day just to survive. And then the world goes dark. The plants die. There's nothing to eat. You're starving. Your species is starving. Without prey, the predators starve too. The tyrannosaurs, those magnificent hunting machines that had ruled for millions of years, they found nothing to hunt. The entire food web, the intricate web of dependencies that held the dinosaur world together, collapsed in weeks. 75% of all species on Earth went extinct. Not gradually over evolutionary time, in weeks, in months, in what geologists call an instant, which actually means maybe a few thousand years, but it might have been much less, possibly as little as weeks. The age of dinosaurs, which had lasted for over 160 million years, ended not with a whimper, but with a cosmic sledgehammer. But the asteroid didn't kill everything. Small things survived. Mammals, tiny creatures no bigger than rats, they made it through. They could hide in burrows. They could survive on almost nothing, on insects and seeds and carrion. They were adaptable. They were the right size to fit through the cracks of a broken world. Birds survived too, though just barely. Only the species that could survive on a devastated planet. A few species of crocodiles and turtles made it through the chaos because they could go for long periods without food and tolerate extreme conditions. Some fish, some insects. But the world they were inheriting was not a world of recovery. It was a world of devastation. The forests were burned away. The sky was still full of ash. The climate was in chaos. Temperatures plummeted as the dust blocked out the sun, dropping as much as 50 degrees in some regions. Then slowly, the climate swung the other way, becoming warmer as trapped greenhouse gases accumulated in the atmosphere. Carbon dioxide and methane and other gases that had been locked up began releasing into the air, and the planet started to heat up again. The world became unstable, violent swings between extremes, hot, then cold, then hot again. Rain patterns shifted. Ecosystems that had been stable for millions of years were disrupted. The survivors were clinging to existence in a planet that was fundamentally hostile, that was actively trying to kill them. But something remarkable happened. Within the first few thousand years after the impact, life started to re-establish itself. Ferns, the hardy survivors that can reproduce from underground runners, even after everything above ground is burned away. These began to spread across the scorched landscape, like green ghosts of a past world. Then flowering plants appeared. Some plants had seeds that could survive the impact winter. Some plants could regenerate from underground root systems. Gradually, over decades and centuries, the barren landscape started to green again. Not the same landscape. Different. Completely different. The plants were different. The seeds and trees that had made up the old forests were gone, incinerated in the global firestorms, their genetic material destroyed, their species extinct. New species were taking their places, new combinations of plants creating new ecosystems never seen before. Different food sources meant different animals, different herbivores, different predator-prey relationships, new ecosystems forming from the ruins of the old world. Herbivores that had fed on conifers and cycads now had to adapt to flowering plants, which were different nutritionally and structurally. Animals that had hunted dinosaurs now had to adjust to hunting much smaller prey. And into this recovering world, the small mammals began to diversify. They had inherited a planet empty of large competitors. The dinosaurs were gone. The terror that had kept them small for 160 million years was gone. The predators that could have killed them in an instant were extinct. The enormous herbivores that had crowded them out were gone. The ecological niches that had been locked up were suddenly open. For the first time in their evolutionary history, mammals could expand. They could grow. They could explore new ways of living. They could become herbivores, predators, tree climbers, ground runners, burrowers, swimmers. Everything suddenly became possible. Some mammals started getting bigger within just a few generations. Not dramatically bigger yet, but measurably bigger. Within 100,000 years, mammal species were noticeably larger than their pre-extinction ancestors. Some lineages branched off into specialized forms. Some became more carnivorous. Some became specialized herbivores. Some became omnivores. The variations multiplied. The diversity exploded, but we can't see most of it happening. And that's when things get mysterious. The Paleocene epoch spans the first 10 million years after the extinction event, a period that should be one of the most important times in mammalian evolution. This is when our distant ancestors stopped being tiny nocturnal creatures hiding in the dark and started becoming the dominant land animals on the planet. This is when the foundation was laid for everything that would eventually come, including primates, including humans. This is when the rules changed completely. But the fossil record from this period is almost incomprehensibly sparse. We have fragments, scattered teeth, a few jawbones, maybe, if we're incredibly lucky, a partial skeleton. From 10 million years of evolution, 10 million years of ecological transformation, from the dawn of the age of mammals to the establishment of the New World Order, we have a handful of fossils, maybe a few hundred specimens total, and most of those are represented by just a few bones. It's as if someone took the most important chapter in mammalian history, tore out most of the pages, and then scattered the remaining fragments across an area the size of a continent. We can see that something happened. We know mammals grew larger. We know they diversified into different ecological roles. Herbivores, predators, tree climbers, ground dwellers. We know they filled the niches left empty by the dinosaurs' extinction, but we can't see how. We can't trace the step-by-step transformation. We have a creature here that's small and generalized, then nothing for 2 million years. Then suddenly we have a specialized herbivore. How did that transformation happen? Did it happen gradually or suddenly? We don't know. We're left with a black box, a process we can infer happened but can't actually observe. We can see the blueprint, but we can't see the construction. Part of this is just bad luck. The Paleocene world was unstable. Volcanic eruptions were common. River courses shifted constantly. Climate fluctuated between warm periods and cool periods, not smoothly, in jumps, sudden shifts from one climate state to another. The geological conditions that are best for fossilization, stable depositional environments, these were rare. Picture it, an animal dies. Instead of being quickly buried in sediment, it would be exposed to scavengers and weather and decay. Hyenas and vultures and insects would tear it apart. Bacteria would break down the soft tissue. The bones would scatter across the landscape. They would weather and crack and eventually turn to dust. Rain would expose them. Sun would bleach them. Within months, they'd be unrecognizable. Within years, they'd be fragments. Within decades, they'd be gone. Fossilization requires a specific sequence of events happening in the right order. The animal has to die in the right place. It has to be buried quickly, usually within hours or days. The sediments that bury it have to be fine-grained. The sediments have to stay undisturbed for millions of years. Minerals have to infiltrate the bone at exactly the right rate, replacing the bone material with stone while preserving the original structure. All of this has to happen perfectly, and during the Paleocene, that sequence of events was disrupted more often than not. But there's another factor: the Paleocene mammals, the ones that were radiating into new forms. Many of them lived in upland forests and grasslands, not in the river deltas and lakes where fossilization is most likely to occur. They were mobile. They were spread across vast territories. When they died, their bodies were far away from the kind of sediments that preserve fossils well. They were living their lives in places where fossilization almost never happens. So we're left with a biased sample. We find fossils from the few animals that happen to die in the right place at the right time. And from those fragments, we try to reconstruct an entire epoch of evolutionary transformation. There's also the mystery of the ghost species. Genetic analysis of modern mammals tells us there should have been far more species during the Paleocene than we've ever found fossils of. The diversity of modern mammals is too great to have come from the handful of lineages we can actually see in the fossil record. Think about how many different types of mammals there are today. Primates, carnivores, ungulates, rodents, bats, whales, elephants. Each of these groups has a deep evolutionary history stretching back millions of years. We have primates alive today that share a common ancestor with other groups going back to the Paleocene. But we can't find that ancestor. We have fossil evidence of early primates in the Eocene and later periods. We have genetic evidence that different primate lineages diverged millions of years ago. But the actual fossil record of that divergence, of the species that lived right at that branch point, it's almost completely absent. Same with carnivores and ungulates and rodents and bats, all with evolutionary histories stretching back to this period. But the intermediate forms, the species that show how one group branched off from another, most of them are gone. There must have been species that lived, evolved, thrived for hundreds of thousands of years, and then disappeared without leaving any trace we've discovered. They're out there in the rocks somewhere, or they've been destroyed by geological processes, or they're just waiting to be found in some undiscovered fossil site. Maybe they're buried in regions we haven't explored well yet. Maybe they're in mountain regions that have since been destroyed by erosion. Maybe they're in environments that simply don't preserve fossils well. But in the meantime, they haunt paleontologists. Ghost species. Evidence that our understanding is incomplete. Proof that we're missing major parts of the story. The Paleocene also saw dramatic climate changes that we don't fully understand. The planet warmed in the early Paleocene, possibly due to massive volcanic eruptions in what is now India. The Deccan Traps, they're called. Enormous outpourings of lava that went on for thousands of years. Enormous quantities of greenhouse gases were pumped into the atmosphere. Carbon dioxide, methane, sulfur dioxide. The air changed composition. The atmosphere became thicker and warmer. Then around 56 million years ago, something even more dramatic happened. global temperatures spiked even higher. We're talking about a warming event where average global temperatures rose by as much as 5 to 8 degrees Celsius in just a few thousand years, maybe even faster. Tropical conditions spread far into the temperate zones. The Arctic became warm enough for crocodiles to thrive and rainforests to grow. Ocean chemistry changed. The oceans became more acidic. Creatures that had adapted to cool, deep waters suddenly found themselves in a world that was too warm. The oxygen levels in the ocean shifted. Many species couldn't adapt fast enough. This event, called the Paleocene-Eocene Thermal Maximum, or PETM, it marks the end of the Paleocene and the beginning of the Eocene. But we don't fully understand why it happened or how ecosystems responded. There are theories: changes in ocean circulation, the atmosphere warming due to methane released from the seafloor, continued volcanism from hotspots. But the exact mechanism is unclear. Scientists are still arguing about which factor was most important, or if it was some combination of all of them. And the fossil record from this period is so sparse that we can barely track which species survived and which went extinct. We see the climate change in the geological record. We see evidence that it happened. We can measure the change in oxygen isotopes in shells that lived through the event. We can see the change in the type of pollen being deposited. We can trace the migration of plants and animals as they shifted their ranges to track their preferred climate zones. But the biological response, the story of how life adapted to this sudden shift, most of that is missing. We know some species went extinct. We know some survived. But we don't know the details. We don't know which adaptations allowed survival. We don't know the order in which species went extinct or evolved new traits. We're seeing the before and after, but not the transition. Imagine watching a movie where a scene is cut out. You see a character in one frame, and in the next frame they're completely transformed. But you don't get to watch the transformation happen. That's what we're dealing with. And that brings us to the Eocene, to a world that was stranger than anything that had come before. The Eocene is a world that seems almost alien compared to the modern Earth. The climate was warm, genuinely warm. Not the kind of warm we get during a heat wave in the summer. Permanently warm. The entire planet was a tropical hothouse. There were no glaciers anywhere on the planet, not on mountains, not near the poles. Even Antarctica had forests, trees growing where there is now ice. Crocodiles swam in what is now Alaska. Palm trees stretched across what is now Canada. Lemurs climbed through rainforests that covered the American Midwest. The Arctic Ocean was warm enough to swim in, sometimes reaching temperatures of 70 or 75 degrees at the surface. For comparison, that's warmer than California beaches. Imagine a world where the climate is so stable and warm that seasons as we know them barely exist. The difference in temperature between the equator and the poles is minimal. Maybe 20 degrees instead of the 100-degree difference we see today. It rains regularly, but not in seasonal patterns. Vegetation grows everywhere. Life is abundant. This is the Eocene, a world of abundance and growth, a world of experiment and diversification. And it should be the best documented period in paleontology. Warm, wet conditions mean lots of plants. Lots of plants mean lots of animals. Lots of animals mean more chance of fossilization. More organisms dying and getting buried and preserved. We should have thousands of fossils from the Eocene. We should be able to see exactly how mammalian evolution proceeded. We should have continuous records of how species changed over time. We should be able to trace the origin of modern animal groups. We should see the ancestors of horses, whales, primates, carnivores, all the major groups of mammals. We should see them changing, adapting, diversifying. Instead, we have massive gaps. The Eocene fossil record is like a documentary with most of the footage cut out. We see one scene where there are primitive early forms of various mammal groups, then nothing for 1 million years. Then another scene where these groups have changed dramatically, then nothing for 2 million years. Then another brief glimpse. And from these disconnected fragments, these brief windows into time, we try to understand what was happening in a period that lasted for 22 million years. 22 million years. That's longer than the entire time period from the asteroid impact that killed the dinosaurs to the beginning of the Eocene. That's longer than the entire Pleistocene, the Ice Age period that shaped modern humanity. 22 million years of mammalian evolution, and we're working with maybe 2 or 3% of the fossil record that we should have. It's like trying to understand human history by reading 3 pages from a history textbook. A few sentences here, a paragraph there. You can get the general outline. But all the details are missing. All the context is missing. All the really important stuff is missing. The Eocene saw the evolution of creatures that have no modern equivalents. The creodons, massive predators that dominated for millions of years and then simply disappeared, replaced by more familiar carnivores like early cats and bears. Some creodons were massive, bigger than modern lions. Others were small and weasel-like. They filled every predatory niche. They were successful. They were abundant. And then they vanished. Why? We don't know. We don't have fossils showing their decline. They're just there in the rocks, and then they're gone. The Brontotherium, enormous herbivores with bizarre Y-shaped horns that looked like something a fantasy artist invented. 6-ton animals with elaborate horn structures that seem almost impractical. They dominated North American and Asian ecosystems during much of the Eocene, and then they disappeared around 34 million years ago. All of them, every species, the entire family went extinct, but we barely see it happening. Ecosystems full of early primates that were experimenting with different ways to live in the trees. Some were small and lemur-like, others were larger and more ape-like. They were testing different strategies for life in the forest: branch running, fruit eating, gum eating, insect hunting, behavioral diversity, ecological diversity. Early whales that still had legs and looked more like otters than the whales we know today. These creatures were transitioning from land to sea. They were developing new adaptations: streamlined bodies, paddle-like limbs, the ability to hold their breath for longer periods. But we don't have fossils showing the details of this transition. We have land-dwelling mammals that are clearly related to whales. We have whales that are clearly aquatic. But the millions of years of gradual change, the intermediate stages, most of them are missing. Early horses that were the size of house cats, small forest dwellers, not even looking particularly horse-like yet. But in their bones, the blueprint was there. Over the course of the Eocene and the epochs that followed, they would grow larger and change shape, and develop the characteristics we associate with modern horses. But in the Eocene itself, we can barely see it happening. The diversity was incredible. The evolutionary experimentation was wild. Life was trying every possible strategy. But we can barely see it happening. The fossil record from the Eocene is fragmentary in ways that seem almost deliberately obstructive. We find a complete skeleton here, which is incredibly lucky. Then nothing for 200,000 years. Then a single jawbone from a completely different species. Then nothing for 500,000 years. Then maybe a few teeth. We're trying to understand the most important episode in mammalian evolution from evidence that's scattered across space and time like puzzle pieces from 1,000 different puzzles mixed together. Even if we managed to reconstruct the picture from the pieces, we wouldn't have all the pieces. We'd be missing huge sections of the image. Part of this is geology. The Eocene was a time of dramatic continental movement. India was colliding with Asia, pushing up the Himalayas. The Alps were rising as Africa moved north. The Atlantic Ocean was expanding, pulling continents apart. Mountains were being built and destroyed. All this tectonic activity was terrible for fossil preservation. The rocks that might have contained fossils were being buried so deep, they got metamorphosed into different rock types, destroying the fossils in the process. Rocks that have been subjected to extreme heat and pressure, the fossils within them don't survive. They get recrystallized. The bone becomes part of the metamorphic rock. The identity of the organism is erased. Or they were being uplifted and exposed to erosion and destroyed that way instead. Vast fossil sites that could have taught us everything are simply gone, melted back into the Earth's mantle, or worn away to nothing by weathering and time. Whole epochs of history reduced to dust, but there's more to it than just geology. Many of the creatures living during the Eocene lived in tropical rainforests, and tropical rainforests are terrible places for preserving fossils. Modern tropical rainforests are among the most biodiverse places on Earth. Millions of species. More life per square mile than almost anywhere else. More animals, more plants, more insects, more fungi. Complete ecosystems stacked in vertical layers from the forest floor to the canopy. But they produce almost no fossils. The soil is acidic and dissolves bones quickly. Bones need to be preserved quickly, or they break down. But rainforest soil is full of acids from decomposing leaves and wood. These acids attack bones, dissolving the minerals that make them hard. The constant growth and decay of vegetation means the ground gets churned up constantly. New roots grow through old soil, disturbing anything buried there. Trees fall and their roots wrench up sediments. The forest is in constant moat, constant change. Bodies decompose rapidly in the heat and humidity. The warm, wet conditions that are so good for life are terrible for preservation. Bacteria work faster. Fungi grow better. Chemical reactions happen more quickly. Scavengers are abundant and efficient. Insects, worms, rodents, all feeding on corpses. When an animal dies in a tropical rainforest, it might as well cease to exist as far as the fossil record is concerned. It will decay completely within weeks or months. It will be eaten. It will be scattered and destroyed. Insects will consume it. Fungi will break it down into their component molecules. Nothing lasts. Very little makes it to fossilization. And many of the most important transitions in mammalian evolution probably happened in these tropical rainforests, in environments that preserve fossils almost never. Most of the Eocene was tropical rainforest. The same conditions that make rainforests so biodiverse are the same conditions that make them terrible for creating fossils. So we're missing exactly the evidence we need most. The creodons appear in the fossil record already fully formed as fierce predators. Their ancestors, the creatures that show their evolutionary origin, they're almost completely absent. We don't see the progression from whatever they evolved from to the massive predators they became. Where did creodons come from? What did the first creodonts look like? Were they small and cat-like? Were they similar to modern carnivores? We don't know because we don't have those fossils. The Brontotheriums show up as already massive, already strange, with no clear transitional forms showing how they evolved from smaller ancestors. What was the first Brontotherium like? We don't know. We assume they evolved from smaller ungulates, But we don't have the fossil evidence to show this transformation. We don't know if it was gradual or sudden. We don't know what environmental conditions drove the evolution of these bizarre creatures with their Y-shaped horns. The primates of the Eocene are diverse and specialized, but the species that show the crucial evolutionary steps from one group to another, they're gone. We know modern primates diverged at some point into different branches. We can see where those branches led. We have living apes and monkeys and lemurs as evidence of where different lineages went. But the actual splitting point, the moment when one group became two groups, the ancestors of each lineage, we're missing those. If we could see those fossil ancestors, we could understand what drove the divergence. What environmental change caused one population to split into two? What new adaptations appeared in each lineage? What did the common ancestor look like? We don't know. The early whales are mysterious. We have clear fossils of terrestrial mammals that are whales' closest living relatives, creatures called artiodactyls, even-toed ungulates. We have clear fossils of modern whales, fully adapted to life in the ocean. But the millions of years of transformation between those 2 points, the actual evolution of limbs into flippers, and the body plan from running on land to swimming in the ocean, we barely see any of it. It was happening during the Eocene, probably in tropical or coastal environments where preservation was poor. We see glimpses. There are a few Eocene fossils that show intermediate characteristics, but the sequence is incomplete. We don't have a clear progression. We don't see what changes happened first. Did whales develop the ability to hold their breath before they developed flippers? Did they develop flippers before their bodies became streamlined? We have to guess because most of the evidence is missing, and so we're left with the outline of evolution, but not the details. The understanding, but not the explanation. The result, but not the process. We know the dinosaurs died and mammals took over. We know life recovered and diversified. We know that from those early mammals came all the mammals alive today. We look at modern mammals and trace their lineages backward through evolutionary time, and we know they all converge on ancestors that lived during the Paleocene and Eocene. But how that transformation happened, step by step, species by species, change by change, most of that is hidden from us. The mechanisms are unclear. The timeline is uncertain. The details are mostly missing. We're left with fragments of understanding, pieces of a vast puzzle where most of the pieces were lost millions of years ago. We can see the starting point and the ending point. We can see where life began after the extinction and where it evolved to by the time the Eocene ended. But the journey between those 2 points, the actual story of transformation and adaptation and diversification, it's mostly lost to time. But the Eocene story had to end. Around 34 million years ago, the climate broke. Something fundamental changed in how the planet worked. The hothouse world that had persisted for 22 million years, that had allowed such an explosion of life and diversity, it started to cool. Not gradually over thousands of years. This change happened relatively quickly, maybe a few 100,000 years, which in geological terms is practically overnight. Global temperatures dropped by as much as 15 degrees Fahrenheit. 15 degrees might not sound like much when you're talking about air temperature. You might not even notice the difference between a 75-degree day and a 60-degree day. But spread that across an entire planet, apply it to ocean temperatures and atmospheric patterns and wind circulation, and suddenly you're talking about a completely different climate system. Ocean currents shifted. The Drake Passage between South America and Antarctica finally opened wide enough to allow the Antarctic circumpolar current to form, isolating Antarctica thermally and preventing warm water from reaching it. Antarctica, which had been forested, which had had rivers running through it, and trees growing and animals living in that warmth, that continent froze solid. Miles of ice accumulated. Glaciers formed where there had been temperate forests. The change was stunning, extraordinary, and it happened in what by most timescales would be a very short period. Within a few 100,000 years, Antarctica went from a place where crocodiles could bask on riverbanks to a frozen wasteland that would remain frozen for the next 30 million years and beyond. The ice sheets reflected sunlight back into space. Positive feedback loops kicked in. More ice meant more reflection, which meant more cooling, which meant more ice forming. The planet locked itself into a new state. And we don't fully understand all the mechanisms. We have theories, good theories, but the fossil record from this critical transition is so fragmentary that we can't verify them completely. This is called the Eocene-Oligocene transition, the boundary between two epochs marked by a fundamental shift in how the planet works. And if we had a complete fossil record, if we had continuous deposits showing exactly what happened year by year, season by season, we could see exactly how ecosystems responded to this change. We could watch which species went extinct as their preferred environments disappeared. We could see which ones adapted and survived. We could trace the evolution of new species that took advantage of the cooler, more seasonal conditions. We could understand one of the most important climate transitions in mammalian history in exquisite detail. Instead, we have fragments. We know the transition happened. We know what the world looked like before and what it looked like after. But the process itself, the moment-by-moment transformation of one climate regime into another, most of that is missing. The Oligocene and Miocene epochs, spanning from 34 million years ago to 5 million years ago, they represent nearly 30 million years of Earth history. 30 million years. That's an almost incomprehensible span of time, nearly 3 times longer than the entire duration of human civilization, nearly 50 times longer than all of recorded human history. Yet our understanding of what was happening during much of this period is almost embarrassingly sparse. We're talking about the time when the modern world was being born. The world we recognize today was taking shape during these epochs. This is when grasslands really started spreading across continents. For most of mammalian history, the world had been dominated by forests, dense, closed canopy ecosystems where survival meant being able to climb, to swing through branches, to navigate vertical spaces. But during the Oligocene and Miocene, something shifted fundamentally. Forests retreated toward the equator, squeezed by the cooling climate. Grasslands expanded. Open spaces emerged where forests had been. Vast plains stretching from horizon to horizon. No trees, no shade, no branches for escaping predators. Different food sources, different predator-prey relationships, different ways of moving, different body shapes. Everything had to change. Animals that had evolved for millions of years to hunt in forests suddenly found themselves in open grasslands with nowhere to hide. They either adapted or they went extinct. Animals that had been adapted for running through forests, dodging between trees, using branches for escape, they suddenly faced a world of open grasslands. What would you do? You'd have to adapt or die. And the mammals did adapt, dramatically. But we barely see it. The transition from forest to grassland was one of the most important ecological shifts in recent Earth history. It's one of the most important shifts in our own evolutionary history, because our ancestors, the apes that would eventually lead to humans, they were evolving during this period. They were adapting to these changing conditions. They were experimenting with different ways to move and eat and live in a world that was becoming less forested and more open. And this is crucial. This is the period where something happened that set our lineage on a unique path. Our ancestors started to behave differently. They developed characteristics that no other ape has, but we can't see it happening. The fossil record from the Oligocene and Miocene is like trying to watch a movie where entire sequences have been removed. We see a forest ecosystem, apes in trees, specialized creatures adapted for forest life, then nothing, darkness, millions of years of missing time. Then suddenly we see a different world, grasslands, a different set of animals, apes that look slightly different, creatures we don't quite recognize, species that seem out of place. Did this transformation happen gradually? Did individual species change step by step over millions of years? Or did it happen in rapid bursts, long periods where nothing changed, then suddenly everything transformed? We don't know. The fossil record is too sparse to tell. We have a few sites that have good preservation. The White River Formation in North America, some locations in Africa, a few spots in Asia. But vast regions of the planet have almost no fossil record from this period. So we know the big picture. Forests disappeared, grasslands appeared, climates shifted, mammal communities changed. But we don't know the details. We don't know which species went extinct or when or why. We don't know which new species appeared or how they evolved from their predecessors. We have to guess. We have to build theories on fragmentary evidence. We have to fill in the enormous gaps with speculation and educated guesses. And most of the time, those guesses turn out to be wrong when new evidence appears. The creatures that lived during the Oligocene and Miocene were bizarre in ways we're only beginning to understand. Entelodonts. Imagine a pig. Now make it huge. 8 feet at the shoulder. Powerful jaws. Teeth designed for crushing bones. Massive build built for power and strength. These were the ruling omnivores of parts of the Oligocene, dominant on North American grasslands for millions of years. They filled the ecological role that large predators and scavengers fill today. And then they disappeared. All of them. Extinct. Every species. We don't see them declining. We don't have fossils showing their gradual disappearance. They're just there in the rocks, abundant and diverse, and then they're gone. What happened? We don't know. The Chalicotheres, 4-legged herbivores with giant claws the size of a human hand or bigger. Long-legged, almost giraffe-like body plans. Strange creatures that persisted for millions of years across multiple continents. We don't even know what they used those claws for. Digging for roots, pulling down branches, fighting, stripping bark from trees. The fossil record is too fragmentary to tell. We have skeletons. We have bone structure. We have evidence they were successful for a very long time. But we don't have context. We don't have enough specimens to understand their behavior or ecology, or why ultimately they failed. The Miocene mammals in North America were dominated by camels and horses and strange deer-like creatures with bizarre antlers. In Europe and Asia, forests retreated more slowly, so forest creatures persisted longer. But everywhere, the world was changing, and the fossil record barely captures that change. The early apes were beginning to evolve during the Oligocene and Miocene. Primitive forms, small apes, not yet looking like modern apes, though you could see the direction evolution was taking, but you could see the characteristics starting to appear in the fossil record. The body structure was changing gradually. The limbs were becoming more adapted for swinging in trees. The faces were changing shape. The teeth were changing in ways that suggest dietary shifts. The brain cases were getting slightly larger. Somewhere in the fossil record of this period is the complete evolutionary story of how apes went from generic primates to the distinctive creatures they are today. But we can barely see it. We have a few fossils from East Africa, some specimens from Asia, a handful from Europe. But Saint of what was happening is invisible to us. Most of the transformation is hidden. The ghost species return here. Genetic analysis tells us that ape lineages were splitting and diverging during this period. Multiple branching events happening as populations isolated and adapted to different environments. Different groups were adapting to different environments. Some were becoming more specialized for tree life. Others were becoming more adapted for living on the ground. By the end of the Miocene, there were multiple ape species spread across Africa, Europe, and Asia. Different sizes, different adaptations, different ways of living. But the fossil record barely shows this diversity. It's like trying to understand a family tree when you only have photographs of a few individuals, and you're missing most of the generations that connect them. The mystery of the apes during the Oligocene and Miocene is particularly frustrating because this is when something incredibly important was happening. This is when the lineage that would lead to us was becoming distinct, becoming different from other apes. But we don't have the fossils that would show us how that difference emerged. We don't have the creatures that bridge the gap between early apes and the distinctive characteristics of our own lineage. They existed. They had to exist. We can work backward from genetic evidence and see that they had to have existed, but we can't find their fossils. Or if they're buried in rock somewhere, we haven't discovered them yet. But then comes the Pliocene, 5 to 2.5 million years ago, and something absolutely remarkable happened. And this is where things get even stranger, because suddenly, walking through the African landscape on 2 legs were creatures that were almost, but not quite, human. The Pliocene is the period when our ancestors underwent one of the most dramatic transformations in mammalian history. They stopped being primarily tree-dwelling and became primarily ground-dwelling. They developed upright walking, bipedalism. This is one of the most distinctive characteristics of humans. It defines us. It's so fundamental to what we are that we don't even have a word for non-bipedal humans. But why did our ancestors develop it? What selective pressure caused them to stand up on 2 legs? What advantage did it provide? Better sight over tall grass, better carrying capacity, more energy efficiency, more efficient long-distance travel. We have theories. So many theories, but no consensus. We don't know. We know it happened. We have fossils that prove it. The famous Lucy, discovered in Ethiopia in 1974, she's a specimen of Australopithecus afarensis, and she lived about 3.2 million years ago. And she was definitely walking upright. You can tell from her skeleton. Her spine, her pelvis, her leg bones all show clear adaptations for bipedal locomotion. She wasn't a perfect walker. She still had some ape-like characteristics. Her arms were still fairly long relative to modern humans. Her hands still had some features adapted for climbing. Her body was probably still adapted for spending time in trees. But she was walking upright. Her brain was still small, about the size of a chimpanzee's. Still the size of an ape's, about 390 milliliters, less than the modern human brain volume of 1,300 milliliters. But she was standing and walking on 2 legs. That's extraordinary. That's a transformation that required changes to basically every part of the skeleton. The pelvis had to shift. The spine had to curve differently. The leg proportions had to change. The feet had to restructure. The center of gravity had to shift. It's a complete reorganization of the body plan. But we don't know why it happened. We don't know what environmental change caused it. We don't know how long the transition took. And we certainly don't see how it developed, because the fossil record from right before Lucy, from the time when our ancestors might have been transitioning from tree-dwelling to ground-dwelling, from around 4.5 to 5 million years ago, that's basically missing. We think it happened between 4 and 5 million years ago based on genetic evidence and a few scattered fossils. We have a few fragments from that period, some teeth from Kenya, skull fragments from Chad, scattered pieces that suggest something was happening. But nothing that shows us the actual transition. How did it happen? Did bipedalism develop gradually over hundreds of thousands of years as populations slowly shifted their locomotion? Did organisms transition slowly from knuckle walking or quadrupedal ape-like locomotion to upright walking through intermediate forms? Or did it happen more quickly in geological terms? Was there a population that suddenly started walking upright, and then the trait became advantageous and spread rapidly? Was upright walking always advantageous, or did it become advantageous later? We don't know. The fossil record doesn't show us. The crucial evidence is missing. After Lucy, things get even more mysterious. The period between 3 and 2 million years ago should be crucial to understanding human evolution. This is absolutely crucial. This is when the genus Homo, our genus, was emerging from Australopithecine ancestors. This is when our direct ancestors were appearing. This is when tool-making innovations begin to show up in the archaeological record. But the fossil record from this period is catastrophically incomplete. We have a handful of specimens, maybe a few dozen fragments total, and many of those are known from just single bones, jaw bones, teeth, occasionally a piece of skull, rarely a partial hand or arm. But the transitions between species are mostly invisible. How did we go from small-brained apes like Australopithecus to larger-brain, early humans? What changes happened first? Did brain size increase first, or did tool-making abilities develop first? When did different groups diverge? What did they look like? We don't know. We're guessing based on fragments. We have some fossils that might be transitional forms. Some scientists argue about which specimens are important and how they should be classified. Some think there were 3 or 4 different human species alive 2 million years ago. Others think there might have been a dozen. Still others think we're missing entire lineages, entire branches of the human family tree that evolved, persisted for hundreds of thousands of years, and then went extinct, without leaving a single fossil we found. Ghost species. Humans that existed, that did human things, that left their mark on the world, but which didn't leave fossils. The Pliocene is absolutely crucial to understanding our own origins, but for the most part, it's hidden from us. We know we went from apes that walked upright, but still had small brains, to creatures that were recognizably human. We know the transformation happened. We can see the endpoints. But the actual journey, the intermediate stages, the details of what changed and why and how, most of that is lost. And then there's the Pleistocene, the Ice Ages, 2.6 million years ago to 11,700 years ago. Nearly 3 million years of glacial advances and retreats. Hundreds of thousands of years of cold, punctuated by shorter warm periods called interglacials. And this is where things get really strange. Because by this point, humans existed. Our species existed. We were walking around on 2 legs, making sophisticated tools, using fire, communicating with language, creating culture, spreading across continents, adapting to diverse environments from tropical forests to Arctic tundra. And we have so little evidence of it. Impossibly little. There should be so much evidence. There should be billions of stone tools scattered across ancient landscapes, layers upon layers of them. There should be hearths, fire sites, butchering locations, animal bones with cut marks showing human processing, evidence of food preparation, campsites, rock shelters occupied repeatedly over thousands of years, thousands upon thousands of archaeological sites, petroglyphs, rock art, evidence of rituals, evidence of burial practices, but we don't have them. Or rather, we have fewer of them than we should. Between 50,000 and 10,000 years ago, there were tens of thousands of humans across multiple continents, possibly hundreds of thousands. They were making tools constantly, making stone tools, bone tools, probably wooden tools. They were hunting, they were processing food, they were creating art, they were living, they were leaving behind evidence of their activities. All that activity should have created an abundant archaeological record. But the archaeological record for this period is sparse in ways that don't make sense. It's like millions of people just vanished. They left almost no trace, nearly incomprehensibly little trace. Part of that is the ice ages themselves. Glaciers advanced across the northern continents multiple times. During peak glaciation, ice sheets up to 2 miles thick covered Canada, northern Europe, and vast stretches of northern Asia. That ice was like a continental bulldozer. It scraped away the surface down to bedrock. It destroyed archaeological sites. It buried evidence under miles of ice and glacial sediment. When the glaciers finally melted, usually over thousands of years, but sometimes in shorter pulses, the landscapes were completely changed. River valleys were carved into different shapes. Mountains were eroded and reshaped. Archaeological sites that might have existed were obliterated. Entire landscapes were rearranged. But humans weren't just living under the ice. They were living in Africa, in Asia, in Australia, in South America, in the tropical regions that were never glaciated, in the places that should have left abundant evidence. Where's all their evidence? Why don't we find it? And here's the really strange part. Many Ice Age human settlements were on the coast, along ocean shorelines, in river deltas, in wetlands, places where you can hunt and fish and gather plant foods, places where land resources meet sea resources, and you get abundance. You can get marine resources, shellfish, fish, sea mammals, seals. You can get terrestrial resources, hunted animals, gathered plants. It's ideal habitat for humans, predictable resources, high population densities, cultural complexity. But during the Ice Ages, sea level was hundreds of feet lower than it is today. All that water was locked up in glaciers covering massive portions of the continents, so the continental shelves were exposed. Vast areas of land that are now underwater. The Bering Land Bridge connecting North America and Asia, that wasn't a narrow strip of tundra. That was thousands of miles of grassland, a whole continent essentially, an entire world of land that no longer exists. Coastal settlements from that period would be underwater now, submerged under hundreds of feet of sediment and ocean. The early inhabitants of the Americas possibly lived on the Bering Land Bridge. Their settlements are now at the bottom of the Pacific Ocean. We're never going to find them without deep-sea archaeology, which is still in its infancy. The Persian Gulf was a river valley, a fertile river valley with lush vegetation and abundance. Now it's underwater, settlements from Ice Age peoples that lived in that valley, that's drowned beneath the Gulf. The Indonesian archipelago was connected. One large landmass called Sunderland, bigger than India, a single connected landscape. Now it's scattered islands with most of the land underwater. Any archaeological sites from the Ice Age inhabitants of that region are now beneath the waves or buried under deep marine sediment. We've lost the evidence, it's gone. And we're missing more than just coastal sites. Even inland, The evidence is strangely sparse, which brings us to the real question. Why are the gaps so enormous? Why is there so much missing? Why don't we have a clear, continuous record of how life evolved, how the planet changed, how humans emerged? The answer is depressingly simple. Fossilization and archaeological preservation are almost incomprehensibly rare, almost impossibly rare. Think about every animal that dies today, every creature that expires in this very moment, right now. Somewhere a deer is collapsing in a forest, a bird is falling from the sky, a fish is stopping to swim, a mouse is being eaten by a hawk. How many of them will leave any trace? How many will still exist as recognizable remains in 10,000 years, let alone 1,000,000? The answer is almost none, effectively zero. For an organism to become a fossil, everything has to go right. Everything. Every single variable. It has to die in the right place, not on a hillside where it will be scattered by scavengers within days, not in open air where it will be exposed, to weathering and sun and rain. Not in a tropical rainforest where the heat and humidity and acidic soil will destroy every trace within weeks. It has to die somewhere protected, somewhere isolated. A riverbed where it can be buried by sediment during a flood. A lake where it sinks into anaerobic mud. A cave where the chemistry is right for preservation. Somewhere it can be buried quickly. Buried and protected before decay organisms and scavengers can destroy it. Before nature recycles the organism back to its component parts. Once buried, it has to stay buried for millions of years undisturbed. Undisturbed by erosion, undisturbed by geological folding, undisturbed by the rearrangement of sedimentary layers that happens constantly across the Earth's surface. But the Earth is violent, constantly violent. Plate tectonics tears continents apart at rates of centimeters per year. Over millions of years, that's thousands of miles. Volcanic eruptions bury and destroy entire landscapes. Metamorphic processes melt fossils back into the earth at high temperatures and pressures. Mountain building fractures and destroys rock layers. Earthquakes shake and shift sediments. Erosion wears everything away. Rivers cut canyons and destroy ancient deposits. Ocean trenches subduct fossils back into the mantle, where they're melted and destroyed at temperatures exceeding 1,000 degrees. The Pacific Ocean floor, for example, is less than 200 million years old. Everything older has been subducted. Millions and millions of years of ocean life, entire ecosystems with creatures we've never seen, all melted back into the Earth's interior. We'll never know what lived there. The evidence has literally disappeared, converted back to its component elements, recycled back into magma. We've lost an entire history, and that's just the big picture destruction. Even smaller scale geological violence destroys fossils. A river changes course and erodes ancient deposits. A hillside collapses and crushes fossil sites. A freeze-thaw cycle cracks bones apart. And soft tissue, don't even bother. Skin, muscles, organs, soft body parts, they decay completely within days or weeks. Except in the rarest of circumstances, they disappear without a trace. So what we're left with are bones and teeth and shells. Hard parts. And from those hard parts, we try to reconstruct entire organisms, entire ecosystems, entire epochs of history. It's like trying to understand a complete human being if all you had was a skeleton. You wouldn't know about the organ systems. You wouldn't understand consciousness or emotion. You wouldn't know how humans communicate or reproduce or build societies. You just have the bones. Same with fossils. We get the hard parts, and from those, we extrapolate the rest. And we're supposed to do this with an incomplete sample. We're supposed to understand 30 million years of evolution from maybe one fossil per 1,000 years. Less than that, actually. Much less. Paleontologists estimate that less than 1% of all fossils that have ever existed have been discovered. 1%. And remember, only a tiny fraction of organisms that ever lived become fossils in the first place. 1 in a million, maybe. Some estimates suggest 1 in a billion, so we're talking about multiple layers of improbability. For every fossil in a museum, there might be 1 trillion organisms that lived and died without leaving any trace. And all this talk of fossils, of geological processes, of preservation, it leads to an uncomfortable realization. There are chapters of Earth history that we will never know about. There are ecosystems that rose and fell without leaving evidence. There are species that evolved, persisted for hundreds of thousands of years, went extinct, and will never be discovered. There are mysteries that can never be solved because the evidence is gone. The rocks that might have contained that evidence have been melted or eroded or subducted or lost to geological violence. And we have to make peace with that. We have to accept that our understanding of Earth's history will always be incomplete, that there are gaps that will never be filled. That the greatest detective story ever told, the story of life on Earth, is written in a language where most of the pages have been lost to time. But somehow, despite all that loss, despite the enormity of what we're missing, despite the impossible odds, we've managed to piece together the outline, the beginning and the end, the major transitions and transformations. We know that life has been evolving for billions of years on this planet. We know that mass extinctions have happened and life has recovered. We know that mammals rose from the ashes of dinosaur extinction. We know that we emerged from mammals. We know that consciousness arose somehow from the natural world. And maybe most importantly, we know how much we don't know. We understand the profound humility that should come from looking back at deep time. We understand that we are recent, we are brief. We are the products of an almost impossibly long chain of contingencies and coincidences. Every human being alive today exists only because of countless chance events stretching back millions of years. Different ancestors finding each other on different continents. Different mutations conferring different advantages. Different environmental shifts pushing evolution in different directions. The slightest change at any point, and none of us would exist. We're all miracles of improbability, living fossils in a sense, carrying in our bodies the history of our species and our lineage and all the life that came before us. Every atom in your body has been recycled millions of times. Atoms that were once part of dinosaurs. Atoms that were once part of the first plants to colonize land. Atoms that were part of ocean life billions of years ago. The very stuff of your being was ancient before you were born. And that's beautiful. That's humbling. That's something to hold on to when we think about the gaps in the fossil record, the vastness of it, the incompleteness of it, the mystery of it. Yes, we're missing most of the evidence. Yes, there are enormous stretches of Earth history that are basically invisible to us. Entire epochs where we know almost nothing. Entire species that lived and died without leaving a trace. But what we do have, the fragments that survived, the fossils that made it through all that destruction and violence and geological upheaval to reach the present, they're telling us an incredible story. The story of transformation, of life adapting and changing and struggling to survive in a universe that's indifferent to its existence. The story of disasters overcome, of extinctions survived, of innovation and evolution, and the relentless drive of organisms to fill every available ecological niche. The story of how a small frightened mammal hiding in a burrow became, through millions of years of change and adaptation, a being capable of wondering about its own origins. And we're part of that story. We're the most recent chapter. We're the beings that can look back at all that history and wonder about it. We're the creatures conscious enough to know that we don't know, conscious enough to know how much we're missing. And perhaps that's the most important thing. Not the fossils we've found, but the questions they inspire. Not the gaps we've filled, but the gaps that remain, challenging us to dig deeper, to search harder, to expand our understanding of the deep past, to be humble in the face of deep time. The dark age before humanity rose, it's still dark. It's still mysterious. It will probably remain largely mysterious. Some evidence is simply gone forever. Some species will never be known. Some evolutionary transitions will never be documented. And we have to make peace with that. We have to accept the limits of our knowledge. But in that darkness, in that mystery, there's something precious. There's room for discovery. There's room for new fossils to be found and to overturn our understanding. There's room for wonder. There's room for questions. There's room for the universe to keep surprising us with its secrets. Every year, new discoveries force us to revise our understanding. Fossils we never expected to find change everything. And that will continue. The dark age before humanity rose will remain mostly dark. But slowly, one discovery at a time, we're learning to read the story written in the rocks. We're learning to understand the message left by creatures that existed in a world we'll never see. We're learning to listen to the Earth's history. And that story, incomplete and mysterious as it is, tells us everything we need to know about who we are and where we came from.